And then if you look, you can see that all of these are filled up right to the line, counting in for the meniscus. Okay, ready to clean off the cuvette before we put it in? Okay. Alrighty. There, put it in. We're going to close the lid. And then come up here. Zero it out.
Our number is this, so we're just going to have to subtract from there. We have these numbers on here, and then where are they at? Oh, they are here, written down for our absorption.
Be sure to clean up any volumetric flasks or beakers that you use to contain any of the solutions we used today, and clean up any spills throughout the experiment. Our first step in using the spectrophotometer for this lab was to scan across all wavelengths of UV-vis light. This can be useful because each substance has its own characteristic absorption spectrum, so this can be used to identify a substance. It can also be used to determine the wavelength at which the most light is absorbed by the substance by locating the lambda max, the highest point on the graph, so it would be this point right here. By scanning across multiple different concentrations of the substance through our dilutions at this particular wavelength, we were able to determine the relationship between absorbance and concentration, which we determined was a direct relationship. So, by using an absorption spectrum, we can also determine the concentration of a substance if we know the absorbance. This is the Beer-Lambert law. It states that the absorbance of a chemical species is equal to the molar absorption coefficient of that species times the molar concentration of that species times the optical path length. Now, the molar absorption coefficient is constant for each chemical species as long as we keep the wavelength of light that is absorbed the same in the spectrophotometer, which we do in this case. And the molar concentration is found by dividing the moles of solute by the liters of solution, so we just calculate molarity as we have been. And the optical path length is the distance traveled by the light through our solution. So in this case, it would just be the distance, the length of our cuvette. Now, the absorbance is measured by finding the difference in the initial intensity of light that is shot through the solution, that is measured before it goes through the solution, and subtracting the final intensity of the light after it has traveled through the solution. Now, because in our case, the wavelength and the chemical species is kept constant, and we use the same dimensions of cuvettes in our spectrophotometer, absorbance and concentration essentially have a direct relationship. Now, in this experiment, we're only interested in the absorbance level of the actual chemical species in all of our solutions. So this is why we had to zero the absorbance of the water in the solution from the absorbance measured of the actual chemical species in the solution. If we hadn't done this, if we hadn't subtracted that absorbance value, the absorbance value measured would be slightly larger than what is actually accurate.